Okay, I think at least almost everybody is here. This session has two students that are still in quarantine, so they couldn't come, and this session should being recorded. And first, I want to welcome everybody to this class, Physics 3041. And this is my first year teaching this course, so please bear with me if you find something wrong, and please let me know immediately, and I will try to fix things if they can be improved immediately. Okay, and this course is Electromagnetic Theory 1, and I believe it's one of your core course in the third year. So please pay a bit more attention and try to do your best, because it takes time to do good in the exams. Okay, before I start the course, I want to go through the syllabus and tell you about how everything should be done. And so first, the most important thing is the textbooks for this course, right? And so for that, you can simply search Physics 3041 in the library, and there should be 3 textbooks that are being already reserved in the library. And so the fifth one, so the third one here is being reserved. All of them are in the course reserve room already, and there are 5 copies of the last one, and the last one is also the most important textbook in this course. And this is, the name is the Introduction to Electrodynamics by David Griffiths. So this textbook has many versions already, and you can find third version or fourth version in the library. I think there are about 3 of them, and you can even find the first version, second version. So there are total 5 copies in the library, and you can borrow one time for 3 days, and that should be enough for you to find what you want to find. And so I reduced the time to 3 days because everybody could take a look at this, and I believe this is a very important textbook, and this is written also excellently. And so this is, I think, one of the best books you can find about physics. So for other courses that you might not be able to find an excellent book like this one, so please cherish this book. And so also you can find the online version at the library. And if you click on this link, and it will show that there is a full text available from the Cambridge University Press. And if you click on that, and you can actually read them online. And but you might be able to find other ways to read. And other resources include the Feynman lectures at caltech.edu. So it's an online digital book, and you can simply click on this link and browse all these chapters of this volume 2. I believe volume 2 is about E&M, and there are also about other chapters of physics. Okay, and now if we look at the syllabus, the first thing pops into your eyes is the course description. And this is quite long, and you might don't need to look at the details, but in short, what we are doing is actually play with Maxwell's equation, and we are also part 1, and there will be part 2 that for Physics 4041, and we'll go into more details. And so there are about 26 lectures in 13 weeks. However, there is 1 day that's vacation, so it's only 25 lectures. And if you subtract 1 midterm, so there are only 24 lectures left. And my schedule, my tentative schedule at least is the following. So I will go through the second and third chapters in about 8 lectures, and this is about electric fields in vacuum. So this is only consider electric field and no magnetic field, and it's a static field. And chapter 4 is additional 3 lectures, and which brings matter into play. And basically, chapter 2, 3, 4 are for the midterms. So the midterm is already should be on October the 18th, and if you want, you can actually really start to prepare for it from now. Okay, and then after the midterm, there are 4 more chapters, and it's about 3 lectures for each chapter. And the finals will cover mostly from chapter 2 to chapter 7, and the chapter 9 will be for educational purposes only, and should be not in the final exam. And if you go to the library, you can actually look for the final exams in the previous years, and there are about, I think, 8 to 9 exams in the previous 10 years. And you can use that as a reference, and the final problems should be very similar to this. And if you can master your if you can already answer everything in the previous year's exam, then I think you don't need to go to the class anymore, and you can do whatever you want. But make sure you have to finish your homeworks. Okay, there's also learning outcomes in this course, and it's also extremely long. And however, I've also shortened them for you. And so the first is to not be plagued by the Maxwell's equations. So try to understand what Maxwell's equations are telling you, and simplify the problems simplify your problem as much as you can. And the second goal is to actually go beyond simply the physics and turn to learn the skills, the mathematical skills, and to solve the problems that you encounter, say, not only in your homework exams, but also in your research. And now the ultimate goal is to actually go beyond the curriculum and go beyond what you learned in your physics class. Now, you may be able to learn why Wi-Fi becomes actually faster and faster. So Wi-Fi 5, and we have been using Wi-Fi 5 for quite a long time, and the new standards of Wi-Fi 6 come out in the recent years, and hopefully after learning this course, you may know why it becomes faster. And the next goal for the also of the physics curriculum is try to for the lifelong goal. Try to be curious and try to apply your skills you learned in this class to everyday life problems. And if you go to industry, I think you might still be able to apply the skills you learned here and try to solve the problems. So I've heard a story that so the software engineering at Google, some of them don't know Taylor's expansions, and somehow physics is the physics major students simply use the Taylor expansion technique in the group meeting. Then all of the engineers are fascinated by this technique, and they don't know where it comes from, and this is the place that you are going to shine, I think. Okay, let's talk about where you can find this course information. So the first, you can simply Google Physics 3041 and the CUHK, and this will take you to this link at the physics department. And if you click on this, there is a very simple list of information about this course. And of course, many of the lecture information such as notes and videos will be posted to the Blackboard. And I think you can access the Blackboard now, and I've already uploaded the first lecture's notes onto the Blackboard. And I'm not sure when, but after today, the video recording of this session also will be uploaded. And I hope that if time permits, I will also try to cut the videos into pieces, like into micro modules for you to digest. If you can look it up more easily. So this course are supposed to be a mixture of online and in person. So the assignments will be graded through the Gradescope, and this is a grading system that can be found at the Blackboard. So on the Blackboard, if you look at the left of the panels, you will notice a link to the Gradescope. And if you click on that link, I believe it will ask you to complete your account sign-ups, and it will ask you to check your emails for setting the password. And after you set your account, you may be able to look for the assignments now. And actually, there is already assignments in there. And I'll talk about this later as we go to the next. Okay, so for the previous CAS exam, I've already told you before, and they are already in the library. And as the course goes along, you can actually try out some of the problems to see if you already mastered the course content. And for the homeworks, I want to stress that you have to complete really independently, and you can discuss about how to do it. But in the end, in the final step, you have to each one of you have to complete by yourself. And you can find many resources for the homework. For example, there are about 2 YouTube channels of solving the homework problems in Griffins, and one of them is called by Hayashi Manabu, and the title is Solving Homework Problems, I believe. And he picked up some of the problems in Griffins and recorded a video of how to solve them. You can, if you really found trouble when you are doing homework, you can try to find similar problems and by looking at the videos, and maybe that will help you. And also we have exercise class, right? And in the exercise class, the TA will also discuss some of the problems that's very similar to the homework. And I believe the exercise class is on Wednesday. So if you the homework will be handed out on every Monday. And so if you can take a look at least of the homeworks either today or tomorrow, then you might be able to make use of the exercise class better. Also, you can actually find almost a lot of solutions to the Griffins problem from the instructor's manual. But I want to warn you that do not simply copy and paste, and there are potentially some errors, and I might simply pick up some of the problem from the Griffins, and where actually the answer in the instructions menu might have some typo, and if you copy this typo, then this is a serious problem. And also you can simply search online for some of the problems, but remember that not everything online is correct, and they may be using a different unit system, and so be careful about the answers that you see online. And there might be some problem you can find online, but the answer is simply not I'm expecting, and you may have serious troubles if you do this. Okay, the last thing I want to talk about is that the homeworks actually might be used later in the class. So if you don't do the homeworks by yourself, you might not know what I'm talking about in class, and so pay attention to the homeworks. And if you don't know, please ask. Either ask TA or send in person or email, or simply ask me. And the homeworks even may appear in exams, so really master the homeworks. Okay, the homework will be 30%, and as I told before, that the homework is weekly homework, and typically it's out on the first Monday and due on the next Monday. And the TA will be grading this homework for about 1 week, so you can see your results at the 2 weeks later. So, which is 2 weeks later when the homework is out first. So the TA only have 1 week's of grading time. And now the late policy is different in the sense that you are allowed to either submit homework in person through the pigeonhole at the classroom 213, or you can simply scan and upload by yourself to the Gradescope. And I highly recommend you doing the upload of homework through the Gradescope by yourself, because if you do that, then you can guarantee that you uploaded the homework correctly. And if you submit through the pigeonhole, you might be risking losing your homeworks. And TAs are not supposed to be responsible for that. So, if you submit your homework through the pigeonhole later, then the deadline, it will not be collected, which means that have zero tolerance on the late for the homeworks that's late if you hand in person. And however, if you submit through Gradescope, there is two. There are, even though there are deadline penalties, but you can still get some scores. So if you miss the deadline by 24 hours, you can only get 50% of the maximum mark. So say that you score 60%, and what you will get is 50% if you miss the deadline by 24 hours. And if you miss the deadline for another 12 hours, the maximum will be 25 only. And you don't get any after 36 hours. So the midterms will be a written exam under its own, October the 18th. And as I told you before, that it will basically cover the chapter 2 to 4. It's about the electoral statistics, and there will be no magnetic field involved, and the final will be 40%, which covers chapter 2 to 7. And do you have any more questions related to this? Okay, so if not, okay, so you're welcome to discuss the homeworks and finish it independently. That's what I told you before. And okay, so the first homework is to simply sign the form about the academic honesty. I think you can already find online about this PDF. So it's the from the Gradescope. And what you need to do is to have the signature and date, name, student ID. And if you don't have, if you cannot sign on your PC, you can simply go to sign.new, and it will take you to an Adobe website where you can simply sign the document online. So it's called. And so this is the URL. Okay, so next is to about how much time should I spend about this course. So the recommended total hours might be different if you talk to different person. And on the syllabus it says exactly 10 hours. And if you ask some senior teachers, they might say that no, 10 hours is definitely not enough. That's the bare minimum. And you should spend more than 10, at least more than 10 hours. And my suggestion is that you might not need more than 10 hours, but please at least spend about 9 hours. So that gives you about 4 hours in class, and including the exercise class. And so you only need to spend about 5 hours in addition for your homeworks and your readings or reviewing the materials. And so the reason that the 9 that I came up with, because your credit, the course credit times 3 hours is actually what you should do on average for all your courses. And because you take about 18 courses, 18 credits, and I'm not sure if that's 15 or 18 credits each week, and that gives you about 45 to 50 hours each week. And also EMM is definitely a core course, and I think it's one of your most important course in this year. And another course is the quantum mechanics, right? And really, please spend some time in this course, and you should not fall below 9 hours. And okay, so some introduction about me. So my name is Yang Qianyan, and I'm a new physics teacher here. So this is my first year arriving at CUHK. So probably most of you are not familiar with me. And my office is at Science Center ground floor, and at room 9. And you can reach me by my phone, office phone, or to email. And but you can also simply come into my office. And I've set up one dedicated hour for consultation. But you can come into my office at any time, or you can simply post your questions online, such as to the Blackboard, and me and the TAs will look at your questions. And so the first class is a bit special, and I will give you some basic introductions and also some reviews on the vector analysis. And the rest of the class will be covering new materials, and I will give you examples accompanying this new material. So it's kind of a mixture of a lecture and a tutorial. And so the class schedule, I think you should already be very aware of, is that it's on Mondays and Thursdays. Mondays is a bit late, and so I hope you are still not hungry and can still listen to me talking. And so the next lecture will be on Thursday, and it's at a different room. I think it's at lecture room 1, so it's just across this door. And I'll arrive slightly earlier, so you could ask me the immediate questions. But there is a class that's 15 minutes apart, so I cannot enter the classroom too early. But I might be standing out at the doors, and this might be the place that you may be able to find me. I will be over there, like outside. Okay. And there are 3 exercise classes on Wednesday, and I believe you already made your choice in the online class scheduling system, right? And there are about 30 people in the first session. So this first session is could be a bit more packed. but some you might not come. So just be prepared. And but I still strongly recommending you coming to the exercise class. And so for the first week of the exercise class, the TA will be talking about the vector analysis, and he will give you some examples. And for the rest of the exercise class, we will go through some examples that's similar to the homeworks. Okay, and so this is some information for the TAs, and so we have actually 4 TAs in this class, and the first TA is Terrace, and so could you stand up or just let everybody know that? So Terrace will be responsible for the first exercise class session, and so he will. Today I will go through the vector analysis very fast, and hopefully Terrace will give you some examples about what I've taught today and on Wednesday. And if you are confused by what I taught you today, then you are strongly recommended to go to the Terrace's exercise class, and he will give you a lot of examples that will help you understand the vector analysis and help you review what you have already learned. And okay, so for the following exercise class, it will be held by the next 3 TAs. So Ken, could you stand up and let everybody know? And Jackie, and Isa. So okay, welcome the TA. So they have already set up the consultation hour, right? So the consultation hour actually is on Tuesday, Thursday, Friday, and you have exercise class on Wednesday, and on Monday you can still find me at the my consultation hour or during the before the class. So you should be able to find us every day throughout the week. So I hope you can make use of this time and try to really learn by conversations or by in person. Okay, so about how to give feedback for this course. The first way is to simply contact us, either me or the TAs in person, or through emails. Or you can, if you are too shy, you can even send anonymous emails. And you can also post a message in the forum, the course website. I'm not sure I've set up in the Blackboard, but the Blackboard is not very well in terms of the forum. I'll try to see if I can find alternatives. And then if you say that you still have a strong mind, like if I'm not listening, you can express your views in the term end course evaluation. But if you find that I'm doing very well, and please really speak up in your term end course evaluation. And that is very important for me, because I'm a new teacher, and the teaching here at CUHK is a really important part of what I'm doing. And finally, if you find that the course evaluation is still not enough, you can also express your views in the staff-student consultation meetings every year. And so you can somehow send a student representative to help you convey the messages. Please ask others how to do that. And what I want to emphasize is that please let me know as early as possible if you find anything confusing or anything that I did wrong, so I can actually correct them or I could improve. And so, for example, I might talk too fast. And if that's the case, please ask me to slow down, saying that sorry that I really didn't. Sometimes I might in a different viewpoint than you, and might not completely understand what you learned before, right? So please ask me to go over some of the materials again, like maybe in a different perspective, if possible. And sometimes I might mumble, or if you cannot hear me, simply please ask me to speak louder or closer to the mic, or sometimes even the mic might break, right? And this is my first time teaching this course, and unfortunately the previous teachers either retired or left CUHK, so I didn't have anything on hand, so all the slides are prepared by myself, and I can imagine that there are a lot of typos on the slides, and maybe some of the examples, and please let me know if possible. You can let me know in class, or if you want, send me emails or in person later. Okay, so some of you might ask, why do we need to learn ENM? Well, what I want to say is that it's actually mathematically beautiful. What I mean is that if you go to courses at a higher level, maybe you can find some things that's very, very long expressions. But here in ENM, the Maxwell expressions equations are really, really simple, and I think that's the most friendly equation that you can find. Even though that's its own 3D geometry, and the cross product might be a bit more difficult to deal with, but still, mathematically speaking, it's still a very elegant expression. And also, the ENM is very special in the sense that the Maxwell's equations are correct everywhere and at any time. And say that for classical mechanics, if you reduce your system scale, the classical mechanics might break down, and you have to go use the quantum mechanics, right? But ENM is actually really correct still in the quantum mechanics level. And say that if you go fast, the classical mechanics again breaks down, and you have to use special, and you have to use relativity. And here, the special relativity also accommodates the ENM very elegantly. And so this is the first aspect of why you need to learn ENM. And the second one is that actually the ENM force is one of the 4 fundamental forces. So the 4 forces that exist in nature only are named gravitational force, electromagnetic force, strong force, and weak force. So you are very familiar with the gravitational force exerted by the Earth, right? And probably you might heard of the strong force and weak force from the nuclear physics. So strong force is really what's the force that binds the quarks in a proton or neutron together. And weak force are responsible for the decays of particles. And these 2 forces typically not quite in our everyday life, because it's hard to break the protons apart, and also you don't see radioactive materials in your everyday life. So really, the strongest force that you feel is the electromagnetic force. That is responsible for your van der Waals binding, and every many materials, and even the friction and all these forces that you think there's are not electromagnetic forces, actually fundamentally electromagnetic forces. And the gravitational force is actually much weaker comparing to the electromagnetic force. And also, if you consider the electricity and the magnetism, the electromagnetic force is actually the first one that's been unified through the classical field theory. And so in order to describe the forces, we use the fields, right? And then if we go to the quantum level and use the quantum field theory, this can take care of the strong force and the weak force. And this is actually really inspired by what the classical field theory has been doing. So really, if you use the quantum field theory, it can incorporate all three forces. And right now, we are still not sure if the gravitational force could be included in a unified theory. And that's what string theory has been doing. And they try to find they are trying to think of a theory that can actually describe all the forces, but there hasn't been experimental observations yet. Okay, and so now you may be convinced that you need to learn E&M in your college, but you might still ask, like, we already studied this in the second year, so in physics 2041, it's introduction to heat and also electromagnetism. So why do we need to learn about this again? So, what I want to say is that in physics 2041, what you learn are very simple problems and with high symmetry. For example, you might be asked how to solve the problem like finding the electric field of an infinitely long line charge. Say, however, here what we might be doing is actually to look at problem with less symmetry. The infinitely long charge might be replaced by this charge of finite length, and if you go to graduate level, and you might even find problems that's even less symmetry and more general. And so here at 3041, sorry, this is the typo. It should be 3. And so at 3041, the problems are still relatively easy to solve. And so also another way is to look at this is to really 3041 combines what you learned from the 2041 and 2051. So you learn a bit of mathematical methods in physics, right? But you are not sure why the hell you learned this. Well, that is actually very useful in this 3041. And we will use a lot of techniques that you learned from this mathematical methods course. And hopefully this will lay a good foundation for you to learn further. So there are courses of 4041, and you can also find the E&M in your graduate level courses. And starting from Physics 3041, I believe what you have learned is very useful already, and this problem-solving skills that you learned in this course are definitely useful for research, for the cutting-edge research, and you will be expected to use what you learned today for if you plan to do some research with some of the professors at the physics department. Okay, now let's try to review what you have learned in the physics 2041 class. So the introduction to the electromagnetism. So in principle, what you have learned it actually can be summarized by 5 equations. So the first one is you can treat this as the definition of the electric field and the magnetic field. So what I mean is that say that we can consider a moving test charge with charge q, and it's moving at the velocity v. Now we can write down the Lorentz force expression as QE plus V cross B, right? And this Lorentz force is actually one of the equations that's accompanying the Maxwell's equation, and you are supposed to use this probably in your exams. And so this one actually defines the electric field and the B field. So say that if you set the test charge at 0 velocity, and you can actually immediately find out the electric field E, right, by dividing out the charge Q. And if you make the charge move, then you can find out what's the magnetic field at that location. So this is how you get the fields from the test charge, right? What this means is actually you are trying to find out the force exerted by these two fields, and how this force comes from is described by the Maxwell's equation. And so in Maxwell's equation, you can find the current, and also you can find the charge density. And so given initial current and the charge density, you can find out all the information about the electric field and the magnetic field. And then from this source, so these fields are generated by some source charge and current distribution. Then you can use from them, you can calculate the E and B field, and then E and the B field can exert additional force on test charge. So it basically what they're doing is to separate the source and test charge interaction by 2 steps. One is to generate the field, and then apply the field to the test charge. Okay, now you may say that, well, the expression that I gave is actually have some integrals, and it's not what I showed before. Like, it's only a what I showed before is only a simple expression like del dot E equals 0 over epsilon naught. And how can you go from the differential expressions, go from the integral expression to the differential equation? Well, you have to use some vector analysis. And now, so for example, you have learned this divergence theorem before, and this also called Gauss theorem, or called Green's theorem, or called simply called the divergence theorem. So what it does is that it relates the field, the flux across the surface, across a closed surface, to the divergence of field inside this volume. And so the surface is actually the surface that's touching this volume, and you can think of the surface simply as the edge of this volume. And so if you are given a ball, and then the outermost shell of this sphere will be your integrating surface. And now if you use this divergence theorem and combine it with the integral version of the Maxwell's equation, and you can simply equate the right-hand side of both two equations, and that gives you this expression over here. And notice that here this volume is actually not simply one volume; it can be any volumes, and because for any volume, for any integral, this one is correct. So we have to, what we can find is that what's inside here is 0. So that's how we derive the differential forms of the Maxwell equation. And this was for the electric field, and we can apply the same thing to the magnetic field, and arrive at del dot B equals 0. Now, from the divergence theorem, we already find out two of the differential forms for this Maxwell equation. Also, we have another one called Stokes theorem. So the Stokes theorem is to relate a surface and also the edge of the surface. And now, if you again combine that with the Maxwell's equation, you can readily find out the differential forms of the Maxwell equation by doing the exact same thing. And for more about divergence theorem and the Stokes theorem and how they can be used in Maxwell equations to give you more insight, you can actually look at this video from 3 Blue 1 Brown. I'm not sure if you have heard of that YouTube channel, but that channel actually has one video specifically about divergence theorem and the Stokes theorem and the application in the Maxwell equations. And here, so I will simply give.
Today, you and I are going to get into divergence and curl. To make sure we're all on the same page, let's begin by talking about vector fields. Essentially, a vector field is what you get if you associate each point in space with a vector, some magnitude and direction. Maybe those vectors represent the velocities of particles of fluid at each point in space, or maybe they represent the force of gravity at many different points in space, or maybe a magnetic field strength.
Okay, so I only give you a 30 seconds preview. So please make sure to watch these videos, and I'll send you a link. I'm not sure. I think it's on a reading list, but let me send you a link later to the Blackboard also. Okay. Now, have you? I'm not sure how many of you still are very familiar with what I've talked about for the divergence theorem and the Stokes theorem. So, if so, could you raise your hand? Say that I'm really very familiar with this. Okay, I see nobody raising hands. So you all forget about what you taught before in the second year, right? So really, you need to pay attention and try to review what you have learned in the 2041 and 2051. Okay, try to read through your notes about the vector algebra, and hopefully that will be very useful for this course. So because I believe that many of you may have forgotten what's in the 2051. So let me simply try to briefly go through what you have learned before. So this is simply actually the material in Griffin's chapter 1. So please also take a look at the chapter 1 of Griffin's if you still not familiar with vector algebra. Many of the identities will that's from the chapter 1 will be used extensively in the later part of the book. So if you are already very familiar with this vector algebra, that will help you save a lot of time when you are doing homeworks. So vector algebra is about vector, right? So for a vector, you can understand it from two perspectives. One is the geometric perspective, say that you can simply replace your vector by a headed line with an arrow, So the direction and the length of this arrow actually determines your vector. And if you view it in this point, the summation of vector is simply connecting the vector head and tail, and say that this is A and this is B. The summation of the two vectors will be from the end to one end to the other's tail, and sorry, from one's end to another's head. And so another way of looking at the vector is simply to decompose into all these components. Say that a vector A actually can be written as three numbers, AX, AY, and AZ. You can also understand this in the sense that you are actually numerically storing three numbers, and however, a vector really goes beyond simply three numbers, and you may be able to find out why in the Griffiths. So a vector Griffiths claims that can be transformed by rotation, and simply not every three numbers can be transformed by rotation. So some basic identities of the vectors involve, like the two vectors can be added, and the addition is commutative and also associative. And the vectors can be multiplied by a scalar, and the multiplication is distributive. And you can define a dot product and of the two vectors. Say that I'm trying to find out the dot product between A and B, and then what I need is simply the magnitude, that is the length of the vector A and the length of vector B, and also the angle between them. And so this theta and the cosine theta is cosine theta is what you need to find out the dot product. And the dot product is also distributive and commutative. So A dot B plus C is simply A dot B plus A dot C. And I'm missing pixel here. And commutative is A dot B is simply B dot A. And now the second product you need to be aware of is the cross product. So the cross product is defined slightly differently. So A cross B is AB and the sine theta, but it's a vector, and there is a direction to the cross product that is unit vector that's perpendicular to both A and B. So say that we want to take the cross product of this two vectors, and you say that x is A is along this way and B is along the other way. So the final vector will be pointing out of the screen, and to know how this y is pointing out of the screen instead of inside the screen, well, it's a convention, and this is a right-hand rule. So remember that we always use the right-hand rule when we're doing the cross product. And so here on the Wikipedia, the right-hand rule is saying the A vector and the B vector and the cross product of the third of the A and B. But I typically don't use this, and what I do is say that you get an A vector, and you point all your forefinger to the A vector, and then what you do is to change your fingers all the way to the B vector, and then what's your thumb pointing is the A cross B direction. And so here, remember that this right-hand rule is simply a convention, and you have to follow everybody's been doing. And really, here, if you get this, then this is what defining the n unit vector, and say that if you do the reverse way, you actually get a minus sign. So remember that this cross product is not commutative at all. So A cross B actually equal to the negative B cross A. And so be careful with this. Now I've talked to you before about the component form, right? You can always write out your vector explicitly in terms of ax, ay, and az. Now if you write down everything in the component form, everything follows straightforwardly. For example, you can readily find out how vector A and vector B sums up together, and that gives you this component form, and you can prove what I talked about before. Everything can be understood in this component form. Now here, when you are multiplying this scalar, you have to multiply the scalar for each component, and if you calculate the dot product, you need to multiply like component. So so this is not A plus B, so it should be A dot B, and so A dot B is actually an AX BX plus AY BY plus AZ BZ. So this means that if you dot two vectors together, what you get is a scalar. And now for the cross product, you should use the determinant, and you should have already learned that from the mathematics course, right? So if you want to write out the cross product of A cross B, you actually need to write out first the directions on the first. I need to write the directions on this first line, and then write the first vector on the second line, and write the second vector in the third line. And now, if we write down this determinant explicitly, we can also get the component form of this expression. Now, if we get a bit more complicated, we can combine the two, right? If we calculate the B cross C and also dot A, this will actually give you a scalar, because B cross C gives you a vector and the A dot vector is a scalar. And this is actually assigned volume of this parallelepiped, and this term is actually means that it's a three-dimensional figure has been formed by a sixth parallelogram. So here A, B, C are simply the vectors that determining this three-dimensional figure, and A dot B cross C simply give you the volume of this 3D image. And now you can try to check that actually it's a very beautiful mathematical form, that you simply replace the directions of x hat, b hat, and z hat with the x, ay, and az, and that gives you the volume. So this is the triple product. Also, I think the most important thing from the triple product is the cross product form. So this actually has a very well-known nickname for this rule. This is remembered as back cab rule. Okay, so what it means is that the cross product of A cross B cross C equals B vector and multiplied by A dot C minus C vector multiplied by A dot B. And you may be able to find this rule in your cheat sheet of the exams, but this rule is extremely important, and you maybe need to use this several times in your homeworks, and so remember to look for this back cab rule. And we will also use this rule in class. okay, let's go next to talk about the gradient. So consider we are familiar with the slopes, right? So slope is really for a single variable functions, and the dt dx will be a slope. Say that the t is only dependent on x. Here, however, the t can be dependent on x, y, and z, even though t itself is a scalar. Now, how do we express the dt in this situation? Well, we can always express the dt in terms of partial t partial x dx plus partial t partial y dy plus partial t partial d dz, right? So that's our starting point. And from this expression, we can actually separate this expression into two terms. One is the dl. So here on the second term, is simply pointing at the infinitesimal line element. So it's dx x hat and dy y hat and dz d hat. Now, what do we need to complete this dt is simply what's left on the left. So if you multiply these two vectors together, only the like components are multiplied. So what's left, what you will get is the one that in the first line. And now what's left over here is actually being defined as a gradient. So it's called del t. And del t, this is the definition of the gradient. And here, what is this del really? And now let's take a closer look at this del. So del is actually a vector. So on LaTeX, should be typed as nabla, but we typically call this a del, or called a del vector. Remember that it associates one partial derivative with one unit vector. So x hat, y hat, and z hat are unit vectors. And if you apply this to a scalar, then a vector applied to a scalar will result a vector, right? So gradient here, what we just looked at, is a vector. And now for the divergence is simply del dot b, and vector dot product gives you a scalar, so a divergence gives you a scalar. And finally, if you do the curl, a curl of a vector, and with another vector is still a vector. So try to be sure if you are dealing with vectors and scalars, and try to avoid any mistakes. So you can further expand on this. In this, you can try to find out how three of them play together. And however, one thing I want to mention to you is that the del operator is not a conventional vector, so you cannot do everything a vector to this del operator. So for example, the del operator is itself a partial derivative, right? So for a derivative, you need to consider the chain rule. So say that if you apply derivative of two functions of f and g, you have to use f derivative g plus g derivative f, right? So similarly, we have to do the same thing here. So if you say that here this is del dot scalar times a vector, then you have to here I'm working in the component form, and in the end, if we work this out, you can find that what's really here in the end is the del operator operating on the scalar first, and this gives vector, and this vector needs to be dotted with the a vector. But however, this is only one piece. Another piece is a plus of f scalar with del dot a. Here, del dot a is already a divergence, and so here really one term in the end becomes two terms, and you have to be careful when you are applying this del operator. And also there are other identities you can find in the first chapter, and I think that many of these identities will be given to you during the exam. So what will be given to you should be on the either the front cover of the Griffins or the back cover of the Griffins. I'll give you more information later of what you maybe find so they can be served as a reference in your exams. Let me see. So one thing I want to mention to you is that about this back cab rule. So for this third term, you see that even though this is a back cab formula, you really need to have actually more terms if there is a del. Okay, so now let's take a look at the second derivative. So what happens if we apply the del operator twice? So there are many ways of how to apply the del operator, right? So say that if you take the gradient and then take the divergence, that's one way. And if you work out in the component form, and you can actually see that the gradient, the divergence of a gradient is actually a scalar, and this scalar has a very beautiful form called partial t squared, partial x squared, partial t squared, partial y squared, partial t squared, partial d squared. And this has a particular name called Laplacian, and you will be using that extensively later. And also there are two identities that you are supposed to use later. So the first identity is the curl of a gradient is always 0, and the second one is the divergence of a curl is always 0. Okay, now we finished the part about the differentials. Now let's go to the integrals. So integrals is really the reverse of the differential, right? And so there are three different kinds of integrals. The first is to do a line integral. That is, what you are familiar with is to calculate the work done by a force along a line, right? So simply what you need to do is to integrate the f dot line element, and then you simply follow the path from the beginning to the end. That gives you the work done by the force, right? And this is we also know that for conservative force, the work done is really independent of the path. It's only determined by the endpoints, right? And in that case, f will be a function. So regardless the path you take, the work will only be determined by this endpoints. And I will give you an example of this later. And for now, let's take a brief look at the surface and the volume integral. So for these two are really the extension of this line integral. So instead of a line element, now you replace the line element with a surface, and then you can find out the flux through the surface, and also you can replace the area element by a volume element, and if you do integration over a scalar, that gives you the volume integral of a scalar. Now, I told you before that for some of the work force that's conservative, that's only been dependent on the two endpoints. And if you look at the gradient of a scalar, that's also the same. So if you calculate the integration of a gradient from point A to point B, what you get in the end is only the Tb minus Ta. That is, the gradient itself is of a scalar is line integral is independent of the path. This means that the gradient of a scalar is a conservative force, and the T here is the potential representing that force, right? For example, for the Earth, the gravity on Earth can be written as a negative gradient of a potential term. So this is minus mg, and this is the conservative force. And so this is pointing. Remember that I should actually written this as a vector, and that will be in the direction of the d direction, and that is. Now, if we integrate and find out the potential, that is simply the mgz, and the t here itself is a scalar, and here this t can be think of as the potential of this conservative force. And this is the theorem of for the fundamental theorem for the gradient, and we have talked about the divergence theorem and the curve theorem before, right? And so these are the three fundamental theorems for differentiation and integration. And now another important trick that I want you to be aware of is the integration by parts. So here you remember that when you do the differentiation of two functions, you need to do the use the chain rule and apply the differentiation to one, and apply the differentiation to the other, right? In the integral, there is a similar thing, and the trick is named. The name of this trick is called the integration by parts. And so you simply do an integral and can derive this integration by parts by yourself. And so what this is useful is that sometimes this differentiation might be not easy to do, and if you find that's really hard, and you can simply transfer the differentiation to the other part that's easier to do, and the price you have to pay is additional term. But this term is actually very user-friendly or friendly to physicists in the sense that we are typically integrating over to infinity or starting from the origin 0. So the expression of this fg at the two boundaries are extremely simple. So if f and g decays at infinity, and if we integrate from say minus infinity to infinity, and what we get is actually a 0. So a lot of times you simply ignore the this second term, but you have to justify why you can ignore this second term. Okay, so we will use this again and again, and it should be you might be able to see that in your homework exams as well. Okay, another topic that I want to cover is the curved linear coordinates. So say that here we are always considering a problem of high symmetries, right? So two special cases with high symmetries is a sphere or a cylinder, and so most likely some of the problems it's easier to work in the spherical coordinates or the cylindrical coordinates, and so you have to be aware of how to transform between the Cartesian coordinate to the spherical or the Cartesian to the cylindrical coordinates. So these transformation laws might be complicated, and if you do this, but you should be able to remember the definitions of the spherical relations. So here this definition should be remembered by yourself, and you also need to remember how to transform from this cylindrical to the from the Cartesian to the cylindrical. And what follows is that you actually need to generalize the derivative also from the Cartesian coordinate to the spherical coordinates or to the cylindrical coordinates. And so here in the Cartesian coordinates, the line element is very simple, right? So it's simply dx x hat plus dy y hat and dz z hat. And everything follows very neat and tight. But if you do this to this spherical coordinates, you might find additional things that you need to consider. Okay, so if I'm not sure if you still remember this slide from 2041, and so here this slide simply discusses how this gradient operator has been obtained. Simply, really, it starts from the same thing, right? So in the Cartesian coordinate, we write down the dv first, and then identify what should be the line element, and from this line element, we can deduce what should be this gradient operator. So this gradient operator is a gradient in the spherical coordinate, and so in order to for the third term to have the partial be partial phi, we need to cancel out this r sine theta, right? So we need to then to multiply here by additional 1 over r sine theta. Okay, so we can do the exact same thing to the spherical coordinates, and the expression is a bit more messy because here for the theta direction it already carries a line element of r factor, and the phi direction also carries a r sine theta factor, and everything follows. And however, this will be given to you during the exam, so you do not need to spend time to re-derive everything. And in your homeworks also you can try to look them up. And however, please be sure to know where you can find this information. Okay, so the last thing I want to talk about today is the Helmholtz theorem. So say that let's consider the first part. Now the claim is that now given a vector f, so it's a vector field, right? So if the curl of the vector field is 0, then it's equivalent to say that the vector field f can be expressed as a gradient of a scalar function v. And actually we already gone through how this arrow can be determined backwards. So to prove the second one, we simply need to apply this del cross to this gradient term, right? And in the earlier sessions, we've shown that here the del cross gradient is always 0. So so here from this arrow we already proved that before, and now what we need to prove is actually the arrow from the to the right direction. And to prove that, we can use Stokes theorem. And if we apply the Stokes theorem to any closed loop of this F field, it gives 0 because the curl of this field is 0 everywhere. And this means that F is actually a conservative force. So remember, we just talked about this a few slides earlier, that you can imagine that F is a gravity force, and correspondingly, the V actually should be the potential energy of this gravity. And formally, we can always define a V field, that is an integration of the F field dot given path L. However, this integration does not depend on what path you take, as long as your two ending points are fixed. Here there is a negative sign because of some convention, and so if you calculate the if you plug in this expression of the Vx, you can find that this identity holds. And now this is the one part of the Helmholtz theorem. The idea is that, say that think of we have an electric field, right? For electric field, the divergence is always zero, and in this case, think of electric field. Sorry, I didn't include it here. So think of this electric field. The curl of this electric field is always zero, and for this electric field, then we can always come up a scalar potential to serve of a potential form of this electric field. And when we are talking about electric field in the electrostatics, and then we can always find a scalar potential, which might be simplifying the problem. And the second part of the Helmholtz theorem is similar but slightly different story, in the sense that now if we look at the problem of del dot F equals 0, so a field that has zero divergence, then in this case the field can be written as a vector potential, a del cross a vector potential. So this should be a plus sign. I'll give you a new note later. So this is a bit hard to prove. So how to prove that is actually in the chapter 5. And if you are interested, you can actually look at the problem 5.30 of the Griffiths, and it will guide you to prove why that's the case. And where this theorem is useful is to think of the B field, right? So for the B field, divergence is 0 in the statical case, and in this case, the B field then can be expressed as a vector's potential, and you can use the vector potential also to simplify your problem. And for a general field that is not similar to a E field or not similar to a B field, for a general field, so we still have the Helmholtz theorem, in the sense that we can always separate a vector field into a field that's similar to the E field and a field similar to a B field. And for the E field part, we can express the scalar and the gradient of a scalar potential. And for the B field part, we can always express this as the curl of a vector potential. Okay, so the last thing that I want to talk about today is some simple notation. Okay, so we can always define a position vector, right? So here in Griffiths, the position vector is called vector R, and it's defined as x times x hat and y times y hat and z times z hat. What this means is that it's calculating the position from the origin to your point x, y, z, right? And now say that we have two position vectors. We can define additional vector called the separation vector. So this is a special notation from Griffiths, and so this is supposed to be I guess it's supposed to be called curly R, and this notation is invented, I think, by Griffiths, and it's not a standard. It's not a standard notation, and say that I'm not sure you have everybody has heard of LaTeX, but LaTeX is a typical tool that's being used to type equations, and it's being widely used in the academics. And in the LaTeX you cannot find this symbol. However, you can define this symbol by yourself. So you can find new macros to define this symbol, and so if you want to type this in LaTeX, you have to look for the tutorials by Griffiths, and so you have to you need to include 2 additional image files that is specifically for this fonts. And now, if you use this separation vector, what's the advantage is that the Coulomb law might be a bit more simpler. So because here in the Coulomb law, we are considering a source charge that's with Q, and a test charge with charge little q, right? And now say that the source charge is sitting at R prime, and a test charge is sitting at R, and this expression will very nicely give the expression for this force between the source and the test charge. And so the argument Griffiths gives is that it will help you write slightly less symbols. But the caveat is that you have to remember what this separation vector means at all times, and be sure that this is really, by definition, the difference of 2 vectors. So you will oftentimes encounter the derivative, right? So say that you can apply the del to this separation vector. You have to specify that whether you want to apply that to the source charge coordinate R, the source charge coordinate R prime, or to the test charge coordinate R. So oftentimes we will use del R to label this label the del operator applying on this R vector, and use del prime or use del R prime to specify that the differentiation should be applied to this R prime vector. So be careful when you are using this notation, and if you're not clear about this notation, you can always write your answers out explicitly and in full. That might be help you to avoid some of the mistakes. Okay, I'll try to summarize what we learned today. So we've gone through the syllabus, right? And I've also give you some motivation about why we want to study E and M. And you can find more details later at the textbook. And we review some of the vector analysis. And if you are not very familiar with this, please make sure to go to the exercise class. And TA Terrace will tell you a bit more examples about in the vector analysis. And there are 2 things that you need to do in the coming weeks. So this is very important, okay? So this is about the homeworks. And so first is to remember to sign your academic honest declaration forms and return to me as soon as possible. So you can get the electronic version through the Gradescope, right? Or alternatively, you can request the form from the TAs. So could you raise your hand, say that if you want to complete your form in the physical form, so I can get an estimate how many of you will use a Gradescope exclusively. So could you raise your hand if you want to do your homeworks in paper and hand in paper, and also hand in the academic honesty form paper? Then please raise your hand. So if nobody raised their hand, then I assume that everyone will be submitting your this academic honesty declaration form online, okay, through a Gradescope, or and also you are supposed to upload your own homework through the Gradescope online, okay, and so the homework 0 is special. So in the sense that this homework is completely online, so you don't need to show me all the steps. Just type your answers on the online, and it will be automatically graded by a Gradescope. And be sure that you understand these questions, and this really try to use what you have learned in this class, to use the divergence theorem and the Stokes theorem to apply to the homework, and to see if you can get the answers. So if you are having troubles getting the answers for this online homework 0, please go to the exercise class, and the TA will help you. So all the homeworks in the following weeks will not be online form, but I will post questions in PDF forms, and you are supposed to find your own paper and try to finish your problems on your paper. And since nobody interested in doing the in handling in the homeworks by paper to the TAs, then I won't talk about how you should get your homework physically to the TAs. And if you really want to turn in your handwritten homeworks to the TAs, please send me an email and let me know. I'll tell you what you need to do in addition, like where you need to write your student ID and names on the paper, because even if you do your homework, even if you hand in your physical homework, me and the TA will still upload it for you to the Gradescope. So if you can upload to your Gradescope by yourself, then it saves a lot of work for us, and also you can guarantee that it's being uploaded correctly. Okay, so in the next I will talk about Coulomb laws and on this Thursday, right? Okay, and so that's pretty much summarized today, and